CPU can directly access, if you have CPU, it can directly access registers and main memory, maybe cache, if cache is present, right? So these are the three main important memory elements in which you can put either the data or instructions, and CPU can access only this. But the problem is all these components are costly. So if you look at registers, they are very costly compared to cache, and if you look at cache, it is costly compared to main memory, right? And main memory is costlier compared to the hard disk, or let us say secondary memory. So main memory is nothing. So now what I mean to say is, when CPU has only the access to these memory parts directly, only these memory parts, but the problem is you cannot go for very large amounts of main memory or very large amounts of register or cache, because your system cost is going to be very, very high, right? And then how much main memory you should really buy, that is one thing. That depending on the main memory, you are supposed to have the system cost also, right? So on your budget, depending on your budget, you are supposed to allocate something to the main memory. How much do you want to allocate? That depends on how much efficiency you want. Okay, what is the relationship between the main memory and the efficiency of CPU is, if you have a bigger main memory, then I could load more process. If I could load more process, if I load more process, then what happens is I could run more processes without stopping. I mean, I'll just take an example and I show you. See, what I mean to say is, if you have more main memory, then the CPU utilization is going to be high. But then I don't really say that CPU utilization is going to be 100% if the main memory is infinite. And that is not what I really mean to say. But then there is some correlation. Just watch it. See, now let us say I have a main memory of 16 MB and a process size of 4 MB, right? Now if I run only one process, if I have only one process, or assume that main memory is 4 MB and a process size is 4 MB, just forget about the operating system. Assume that operating system is already separately present in above the main memory in some other element, and my main memory is 4 MB completely available for the process which contains 4 MB. Then how many processes can I run? Only one process, right? Now if the process, this particular process, spends a fraction of p time doing IO, which means if you schedule the process, it will just spend a fraction of p time doing the IO, then what will be the CPU utilization? Then CPU utilization is equal to, see, what is CPU utilization? The amount of time that you are going to use CPU running the program, right? But the program is saying that I need only 1 minus p fraction of time doing the CPU and the other p fraction of the time doing IO. Therefore, in that case, CPU utilization is going to be 1 minus p. Got it? What I mean to say is, if you have only one process in the main memory, or if the main memory is having a space to hold only one process, this is the process size. If the main memory is having space to hold only one process, then the problem with such a kind of arrangement is, if the process is going to take p fraction of time doing IO, then CPU utilization is going to be 1 minus p, isn't it? Now if this p fraction is going to be 80%, which means if the process is going to spend 80% of the time doing IO, then what is CPU utilization? Just 20%, right? When p equal to 80%, isn't it? So there is a problem. Now CPU utilization is directly linked to the number of processes that can be present in this. Now let us say I am going to increase the main memory size to 16 MB. Then each process size is 4 MB. This is the main memory size and this is the process size. Then how many processes can I put? I can put 4 processes, isn't it? Now again, if each process is going to spend p fraction of time doing the IO, right, then what is the probability that all the processes will do IO at the same time? If p is the fraction of time each one is doing IO, then the fraction of time, the probability that all of them will do IO simultaneously is p power 4, right? And what is the fraction of time that CPU will be busy? 1 minus p power 4. In this case, CPU utilization is going to be this much, right? If I increase the number of processes which are present in the main memory, then the CPU, what it will do is, whenever one process goes for IO, it can choose the other process, right? The probability that all of them will be waiting for the IO is p power 4. Therefore, the CPU utilization in this case is equal to 1 minus this one. So if you assume that the fraction of time each process waits is 80%, then this is roughly equal to 60%. So with 4 processes in the main memory, I have increased the we are getting a utilization of 60%. Now let's see if I still try to increase it. Let us say from 16 I increase it to 32 MB, right? And each process is of size 4 MB. Then how many processes can I get? I can get 8 processes. 8 processes, and assume that the same p fraction of time each one is waiting for IO. Then CPU utilization in this case, CPU utilization is going to be 1 minus p power 8, right? And it is roughly going to be 83%. Got it? So as I increase the main memory size, the number of processes that are going to be present in the main memory are increasing, and hence the CPU utilization is increasing, right? Will it happen like this? I mean, when I double the number of this process, it is going to be like this. So let us say I just want to examine one more. Let us say the main memory is now 48 MB, and each process size is 4 MB. This is main memory size, and this is the process size, and each process is waiting for p fraction of time for IO. Then how many processes can be present? 12 processes can be present in the main memory at the same time. Then what is the probability that all the 12 processes will go for IO? P power 12. Then what is CPU utilization in that case? In that case, CPU utilization is going to be 1 minus p power 12. So if you put 80%, if p equal to 80% of the fraction of the time it is waiting for IO, then we are going to get 93% roughly, right? So if you look at this gain, if it is 16 MB, then it is 60%. If I increase it by 16 MB, then gain is 23%. But if I increase it by one more 16 MB, the gain is not 23%, it is roughly 10%. Therefore, the gain is not going to increase linearly with the increase of the main memory. In fact, you can think of the CPU utilization like this. CPU utilization is 1 minus p power n, where p is on average the fraction of time every process is waiting for IO, assuming that n is the total number of processes in the main memory. I told you, what is n? The number of processes that can be present in main memory at any time is nothing but the degree of multiprogramming, isn't it? Therefore, CPU utilization is directly depending on, or somehow it is depending on, degree of multiprogramming. If you increase the degree of multiprogramming, CPU utilization is going to increase, right? So if I want CPU utilization to be 100%, see, what is P? P is the fraction of time for which it is going to go for IO, and P is obviously a number between 0 and 1. It is a fraction, isn't it? Then what happens is, if I increase the degree of this multiprogramming, if I say limit n tends to infinity, which means if I increase the number of processes that are present in the main memory to infinity, then CPU utilization is going to be, can you guess it? If this n tends to infinity, it is a fraction, it is a number less than 1, then this number will tend to 0, then CPU utilization will become 100% or 1, isn't it? So if you have to get 100% CPU utilization, this formula says that have as many processes as possible in the main memory. But how is that possible? Only if you have lot of main memory, then only you can have lots of processes, right? But then the problem is, if I have infinite main memory, it is obviously not possible, right? The reason is it is going to be very, very costly. So having finite amount of memory, we should try to increase the degree of multiprogramming. How is that possible? Use the memory in such a way that it mimics or it acts as if it is infinite. Got it? Which means even though I have a finite amount of memory, I'll try to use it as if there are infinite number of process or lots of process in this finite amount of memory by using memory management techniques, right? So memory management is all about that. How could you increase the CPU utilization? By putting as many process in the main memory as possible, right? But now it is going to lead to many problems. The problem is this: when you have only one process in the main memory, you can directly take the process, put it in the main memory, execute it, pull it out, fine. But when you have more than one process present in the memory simultaneously, then lots of issues will come into picture. How much memory are you going to allocate to each process? And how are you going to allocate it? How are you going to deallocate it, right? And how are you going to provide the protection among various processes? These are all the various things which you might have to look at it, right? Therefore, memory manager is not just responsible for allocating the memory and deallocating the memory. It is also responsible for providing security, right? There are various things that the memory manager has to look at. So before that, let's see how a program is converted to a process. I think you know the difference between program and process. If you write a code and execute it, and you compile it and you convert it into a machine language, that is called a program, executable code. That will be present in the hard disk. Now if you want to run it, you should convert that program into a process and load it into the main memory and run it. Therefore, there are various modules which are going to be helpful there. We shall talk about all the modules. The modules are like linking, loading, assembler, compiler, all this. Right? Let's see all those things. But anyway, one thing you should observe is, in order to increase the CPU utilization, we have to efficiently use the main memory available. And for that, we should do memory management efficiently. We should implement the memory manager. So we should look at all these things one by one.